Okay, let's dive into this. When you watch a Hollywood blockbuster about a supervolcano, they almost always show the exact same sequence of events, right? People are just going about their day, and then boom, a sudden, unheralded, massive explosion completely out of nowhere. But the science tells a very different and frankly, a much more terrifying story. In this explainer, we are going to completely shatter that myth, because the countdown to a planetary scale crisis, it doesn't actually begin with a sudden bang.
Instead, the real horror begins with absolute silence. You see, in that final hour before a global volcanic catastrophe, the rapid upward grind of this highly viscous, gas-saturated magma actually comes to a temporary halt beneath the crust. It's an eerie, dead quiet. But make no mistake, this stabilization is definitely not a sign of dormancy. It's actually the final structural lock holding back an absolute nightmare.
Section 1. Anatomy of a sleeping monster. To really understand why this temporary silence is so incredibly dangerous, we first need to establish the mind-boggling scale of the threat that's resting just a few miles beneath our feet. Think about the sheer difference in scale and structure we're dealing with here. A traditional stratovolcano, like Mount St. Helens or your classic steep volcanic cone, has a relatively narrow central conduit that vents runny liquid lava. But a megavolcano, it's an entirely different beast altogether. It's an expansive subterranean network of melt lenses and crystalline mush that spans anywhere from 30 to 50 miles across, and it's capped by a massive depressed basin called a caldera. And the magma inside isn't running at all. It's highly silicic or rhyolitic. That means it's incredibly viscous. It's sticky. It basically acts like a gigantic 50-mile-wide subterranean sponge that's trapping immense amounts of dissolved water vapor, carbon dioxide, and sulfur dioxide. So, what's actually keeping this massive, highly explosive mixture contained? Well, it all comes down to this single, absolutely crucial concept: lithostatic pressure. This is the crushing weight of the miles of solid rock comprising the Earth's crust that sits directly on top of the magma chamber. This crust acts as a massive structural lid. The eruption literally cannot begin until the internal volatile gas pressure completely overcomes this lithostatic weight. It's a high-stakes geological standoff. You have a massive volume of highly buoyant magma pushing up against a massive but decaying structural lid.
Section 2. The Earth begins breathing. Now, what's really interesting about this is that as the magma pushes up, the ground above the chamber doesn't just uniformly balloon upwards like a tire. We get a rapid, violent change as we approach that critical eruptive threshold. Because of the immense hydrodynamic lift of the rising magma body, we see something called resurgent doming. This is where hundreds of square miles of land swell upward by several meters, but it causes violent, localized tilting of discrete fault blocks. At the exact same time, we've got hydrothermal decay going on. Highly acidic magmatic fluids literally eat away at the hard rock lid, chemically transforming solid rock into soft, terribly weak clay. And to top the whole shebang off, we get seismic swarms.
Thousands. That is the number of continuous, low-magnitude, harmonic tremors occurring simultaneously. You see, seismologists tracking a super-eruption aren't sitting around waiting for one massive earthquake. They're listening for a continuous, humming vibration. It happens as the incredibly viscous magma mechanically fractures solid rock to force its pathway upward. So the Earth is literally humming, the crust is rotting into clay, and the ground is violently tilting. Section 3. The deadly depressurization trap. With all these terrifying precursors happening, it really begs the question, why don't we just engineer a solution? Actually, there was a widely discussed $3.5 billion space agency proposal to drill a 10-kilometer deep well right into a supervolcano to vent the pressure and cool it down. Sounds like a logical fix, right? Just letting the steam out. But consider this brilliant analogy. It's like the gas in a shaken soda bottle. It's dissolved until you release the pressure, then it all bubbles out. This perfectly illustrates the concept of supercritical fluids. Deep within that reservoir, the magmatic volatiles aren't just floating around as separate little gas pockets. Because of the extreme heat and that crushing lithostatic pressure, the gases dissolve directly into the liquid rhyolite. They are one and the same. There is literally no physical distinction between liquid and gas in this state. So the crucial point here is what happens when you introduce human intervention. The expected outcome of drilling a 10-kilometer relief vent is cooling the chamber by 35%, which would theoretically increase the magma's viscosity. But the actual reality? You trigger a runaway decompression wave. Drilling a hole doesn't act as a slow bleed valve at all. Instead, it removes the confining lithostatic pressure locally, and that instantly forces those dissolved supercritical fluids to exsolve, meaning they rapidly come out of solution and expand violently all at once. Because the rhyolitic magma is so incredibly thick and sticky, those newly formed bubbles can't just escape quietly to the surface. They remain trapped, driving a massive volume expansion that literally tears the magma apart from the inside. Therefore, a drop in pressure actually makes the system far more explosive. Attempting to diffuse the supervolcano by releasing pressure is the exact mechanism that would detonate it. This means the absence of small release eruptions isn't a good thing. It's actually the most terrifying sign of all. It means the system is fully sealed, and the soda bottle is violently shaking. Section 4, the final 60 minutes. The final hour triggers like a rapidly falling house of cards, building minute by excruciating minute into a planetary catastrophe. First, a tectonic fracture opens up, causing a hydrothermal breach. Superheated groundwater sitting just above the magma, which was kept liquid by immense pressure, boils instantly. This rapid phase transition generates a massive phreatic failure. It's essentially a steam explosion that violently shatters the remaining capstone rock. This is exactly like unscrewing the lid off a boiling pressure cooker. Instantly, the lithostatic pressure on the underlying chamber drops. This causes runaway frothing. The dissolved gases exsolve violently, transforming the viscous magma into a highly pressurized, turbulent froth. And finally, deprived of its structural support, the massive rock roof above, which remember is already weakened to clay, suffers a total structural collapse. And this brilliantly illustrates the aftermath. To really grasp the sheer scale of that collapse, look at the Long Valley caldera in California. It's a massive, depressed basin formed after a catastrophic roof collapse, just like the one we're talking about. Imagine an area 30 to 50 miles wide, literally entire mountain ranges, plunging downwards into the evacuating magma chamber beneath it. That is the unfathomable scale of the structural failure we are dealing with here. As that 50-mile-wide roof collapses along the ring fractures, it acts exactly like a giant piston. It violently squeezes the highly fragmented, gas-buoyant pyroclastic mixture right out of the earth. In an instant, a confined magma chamber transforms into a colossal Plinian eruption column, screaming into the stratosphere at near magmatic temperatures. This pumps millions of tons of ash and sulfur dioxide into the sky, initiating a decadal global volcanic winter. Section 5. A seamless cosmic bridge. So, a mega-volcano is the ultimate geological reset button, devastating agricultural production and inducing severe climate anomalies right across the entire planet. But as the ash settles and the world plunges into a freezing decadal winter, an entirely new psychological loop opens up above us. Because the sudden redistribution of mass on the Earth's crust destabilizes much more than just the climate down here. It forces us to ask a terrifying question. What happens when an even older cosmic threat begins altering our planet from above? As the stratosphere darkens, our atmospheric shielding fails, exposing the planet to a mechanism entirely alien to Earth.